Now we're going to look at hydrocarbons, and these are compounds that contain only carbon and hydrogen. And the first group of hydrocarbons we'll look at are the alkanes. Now these are saturated compounds, which means they do not contain multiple bonds, they only contain single bonds. As in this example here, you can see the carbons are completely saturated with hydrogens. We can't get any more hydrogens on, they are saturated compounds. Now, alkanes come from crude oil, and crude oil is a mixture of lots of different hydrocarbons, lots of different size hydrocarbons, and before it can be used, we need to separate those different size hydrocarbons, and we can do that by a process called fractional distillation. Now that's done in a fractionating column like this, which is hot at the bottom of the column. And it's cooler at the top. And it separates the compounds based on their boiling points. The lighter, shorter chain hydrocarbons rise to the top because they have a lower boiling point, and the longer chains, heavier fractions, stay at the bottom. They have higher boiling points. Now, why do they have different boiling points? Well, it's all to do with the intermolecular forces, and the intermolecular forces at play with alkanes are van der Waals. Now, if we take a long chain molecule, between different long chain molecules, there are lots of contact points for the van der Waals forces, and these van der Waals forces build up and make quite strong forces in which to overcome. So lots of energy is required to overcome these van der Waals forces, which leads to high boiling points for the longer chain ones. And lots of energy is required to overcome those forces. Now, for shorter chain alkanes, there are fewer contact points between molecules. As a result, the intermolecular forces, the van der Waals forces, are weaker, and less energy is required to overcome them, which leads to low boiling points. Now, for petrol, straight chain alkanes are not very good fuels. It's much better to have branched ones. Now, you can change straight chain alkanes into branched ones by a process called isomerization. And in this example, we can think of a straight chain pentane, 5 carbons. If you put it through the isomerization process, you'll form 2,2-dimethylpropane, a branched isomer of pentane. And that's a much better fuel since it's got a higher octane rating, it's more efficient, and it does not pre-ignite. There is another process that improves the fuel, and that's reforming. Now you can think of reforming as ring forming. If we take pentane again, straight chain pentane, and reform it, we can make cyclopentane, and we lose hydrogen. Now the hydrogen can be of use in other processes, for example in the making of margarine, which we'll come on to when we do alkenes. So these also do not pre-ignite, and they have a higher octane value. Now we're going to move on to another type of hydrocarbon, which are the alkenes. Now these are unsaturated compounds, which means they contain a carbon-carbon multiple bond. And they do contain at least one carbon-carbon double bond. This is an example of an alkene. This one contains 2 sets of carbon-carbon double bonds. Now these are obtained from cracking of long chain alkanes. And that is the breaking down of long chain alkanes into more useful shorter chain material. Now we go back to our alkanes and our fractionating column. What we're talking about here is we take longer chain material that's at the bottom of the fractionating column, take that out, and we subject it to high temperatures with a catalyst, and we can break it down into shorter chain alkanes. I can give you an example here. If we start off with a 10 carbon molecule alkane, which is decane, C10H22, we subject that to high temperatures along with the catalyst. It will break down, and it will break down into, for example, octane, which is C8H18, and you will get an alkene produced, and in this case it's ethene, C2H4. In cracking you will always make an alkane and an alkene. So these alkenes are useful, as we'll find out now. Before we go on to the reactions of alkenes, we'll have a look at the bond angles and shapes that result from alkenes. This is propene, so it contains one C-C double bond and one C-C single bond. If we look around the double bond, the angles are 120 degrees all the way around the C-C double bond, and that gives rise to a trigonal planar shape around the carbon-carbon double bond. Now we look at the other part of the molecule, which doesn't contain the carbon-carbon double bond. It's a carbon-carbon single bond. The bond angles are 109.5 degrees and make a tetrahedral shape. Now we can look at the reactions of alkenes, and to do that we'll start on a fresh sheet of paper, I think. So to look at the reactions of alkenes, we'll start off with propene as our example. But all the alkenes will react in the same way. It's all a case of the double-double carbon-carbon double bond springing open. So in this case we'll look at chlorine, the addition of chlorine by electrophilic addition, not substitution. And the two chlorine atoms will add across the carbon-carbon double bond and produce 1,2-dichloropropane. Now similarly, oh yes, all these reactions are addition reactions. It's all about things adding across the carbon-carbon double bond. Now similarly, bromine can behave in the same way as chlorine. Now this is actually a test for unsaturation. So if you've got a compound and you don't know if it contains a carbon-carbon double bond, you add bromine water, and if the bromine water discolors, then you have an unsaturated compound. Another one is the hydrogenation of propene. You need a nickel catalyst for this, and 150 degrees Celsius. And the hydrogen just adds across the carbon-carbon double bond and produces a saturated alkane, in this case propane. Now this reaction is used in the manufacture of margarine, where you take unsaturated vegetable oils and hydrogenate them, and they turn into saturated compounds which are spreadable. Now you can do hydration of an alkene as well. You need water in the form of steam with phosphoric acid catalyst at 60 atmospheres pressure and 300 degrees Celsius. So it requires quite a lot of energy, this process. And you can actually end up with two products, because the OH could add on to the second carbon, as it has done here, to produce propan-2-ol. Alternatively, the double bond can spring open another way, and the OH can add on to the first carbon. So in this case, the OH group will add on to the first carbon, and so produce propan-1-ol. So in that reaction you get two different products. Now this is similar to what happens when you react it with hydrogen bromide, HBr gas. The HBr can add on in two different ways. So the Br could add on, whoops, let's change that moment. Rip that out. Now the Br could add on to the first carbon or the second carbon, in this case the second carbon, or the first carbon like this one. So you end up with two products. You could end up with 2-bromopropane or 1-bromopropane. Now the important thing to remember with all this is that all the alkenes react in the same way. If the molecule's got a double bond, carbon-carbon double bond, these reactions will take place.